general form of an exponential looks like this. Y equals a, b, and then to the x power. Whenever you have an exponential, you're going to have a variable in an exponent. That's why it's called exponential. And then just at the bottom, it just gives you a couple pieces of information here. So it says x has to be a real number. You can't put imaginary numbers as exponents on any of these. And it says a can't be equal to 0. So usually you'll see two numbers. I'm going to get to these graphs here in a second. The a value in both of these is just 1, but it might be two separate numbers that you see together. And then it says a can't be 0, because if a would be 0, that would wipe the whole thing out, and you would just have y equals 0. All right, b has to be greater than 0. All that means is b has to be positive. That's what that means. It can't be equal to 0. Again, if it was equal to 0, that would just wipe the whole thing out. It has to be a positive value. You can't take a negative, in this case, you can't take a negative number to an exponent for an exponential. And then b can't be 1. So if b was 1, in that scenario, you take 1 to any power, it stays 1. So that's why b cannot be equal to 1. It can be a decimal or a fraction that's smaller than 1, but it cannot be equal to 1 because that would also just create a line. All right, so we're just going to do some basic introduction to kind of what these look like. So I'm going to write, and you don't have to write this at all. This says y equals 3 to the x. Really, in this scenario, the a value is 1, and they're just not writing that in there. And then we're going to take 3 to the x. And the one right next to this, in that format that I wrote above, 1 is really the a value. It's just not being written in that particular equation because it would be not a situation where that would affect that. But both of these have an a value of 1. All right, so this a is 1. My b value is whatever's being taken to the exponent. For this one, it's 3. On this one, a is 1. And for this one, b is 1/3. So we're just going to kind of get a general idea of what these graphs look like. Okay, best thing I could ever tell you to do if you have to draw a graph is let's just make a little table. And really good idea for a table, especially if a graph, we're not shifted or anything like that. I don't have like scooched over to the right or left, anything. It's just y equals 3 to the x. What I would tell you to do a table. You got -2, -1, 0, 1, and 2. That is a really good basic table for any graph that you'd want to do. Couple negative, couple positive, and 0. And you can pick any x values that you want to plug into this. There's no restriction. It just can't be an imaginary number, which we wouldn't plug in anyway. But we're going to plug in, these are a good example of what the graph should look like if you can plot those 5 points. So I'm literally just going to plug this in. So I'm just going to do 3 to the -2. We'll do 3 to the -1. We'll do 3 to the 0, 3 to the first, and 3 to the second. Okay, so I'm going to start at the bottom of the graph. So you guys, bless you, I know you know these. So 3 squared is 9. 3 to the first is 3. What's anything to the 0 power? 1. So this will be the point 0, 1. Now, okay, don't forget this from our last unit. We did some exponents, right? So a negative exponent is not a negative number. In this case, 3 to the -1, if you guys remember, we can write that as 1/3 to the first to get rid of that negative exponent. So these are just going to be fractions. This would be 1/3 if I plug in -1. If we plug in -2, that'd be 1/3 squared. So it's not a negative number, it's just going to be a fraction. And as I would keep going, those fractions would get tinier, tinier, and tinier. So like if I did -3, it'd be 1/27. If I did -4, it'd be 1/81. So tinier, tinier fractions. Now, if you got a fraction, or if you want to write it as a decimal, that's totally fine with me. Just kind of estimate where that would fall on the graph. So like -2 is pretty close to the x-axis. -1's at 1/3, so maybe kind of try to divide that line up in 3, I don't know. 0, 1 is a nice point. And then I have 1, 3, that'll be a nice point. And then I'll have 2, 9. And this will give you guys an idea of the general shape. If I plugged in 3, and it's going to be off the graph, but I just want you to think about this for a second. If I plugged in 3, the next coordinate would be 27. So it would be like way off this graph. this makes kind of like a J shape is how I would describe it. So it gets really tall really fast. And I'm going to grab a highlighter really quick. We're going to get really close to the x-axis, but we're actually not going to touch it, and we're not going to go over it because I'm never going to have a negative y value, because even I can plug in negative 100 as my exponent. It would just be a super tiny fraction, so it never actually touches the x-axis or goes over it. It's just tinier and tinier and tinier fractions. It would get harder and harder to graph the closer you would get, but it would not actually touch the x-axis. So I'm just going to kind of underline that real quick. All right, so let's switch over to this one. So in this one, my a value is 1 again, but now my b value is a fraction here. It's okay for the b value to be fraction or a decimal. It just can't be negative. So I'm going to use those same table values. -2, -1, 0, 1, 2. Okay. And then to the side, let me come over here. So I'm doing 1/3, and we pick the x values to that power. So if I did 1/3 squared, I just want you guys to think about this for a second. So we'd square the top, right? So that'd be 1. And we'd square the bottom. So that would be 9. So this is going to be 1/9. If I did 1/3 to the first, that would just be 1/3. If I did 1/3 to the 0, anything to the 0 power is a 1. And then these get a little bit tricky. So if I do 1/3 to the -1 power, and you could just type this in your calculator if you wanted to, but what I want you to think about here, this is going to give a -1 exponent, so I'd have 1 to the -1, 3 to the -1. What would happen there is both of those guys would switch places to lose the negative exponent, so I would end up with 3/1. So that's why these values, when you plug in that negative exponent, what it's doing, it's going to flip that fraction over, and it's actually going to make that y value larger. So if I do like 1/3 to the -2 power, it's 1 to the -2 over 3 to the -2. 1 to any power is 1, but this becomes 3 squared over 1, which is why this is going to be 9. So you're guys going to see kind of like a mirror image of what we just graphed. It's just going to be reflected over the y-axis. So here, -2 is at a nice point at 9. -1 is at a nice point at 3. Also goes through, oh shoot, pretend I didn't put that point, 0, 1. And then it goes through 1/3, just kind of estimate, and then +2, 1/9. Again, we're getting really close to the x-axis as we plug in larger x values there, but it's not going to touch it. It's not going to go over it. You're never going to have a negative y value. And so that guy is also a similar shape, but flipped over. So it's like a backwards J shape. And that's going to happen anytime your b value is between 0 and 1. So that's what we're going to talk about just right underneath here. So you have an example of each. In this one, my b value is 3, right? So both of these require, we'll deal with different things tomorrow, but the a value in this situation has to be positive. If the a value is negative, we'll talk about that tomorrow. The a value is going to be positive. Then if your b value is bigger than 1, you have this first graph, which is going to be exponential growth. All right, the second graph we did, the b value is between 0 and 1, so like a 1/2, 1/3 in our example, like 0.25, something like that. If you have that, that's going to create a graph of what we call exponential decay. So exponential growth, that first graph that starts small and gets big really fast, exponential decay on the negative side is going to start high up in the air, and then as you increase your x values, it's going to get closer and closer to the x-axis. So those are the two graphs that we have there. Now, as you guys are looking, I'm going to try to keep this on the screen if I can. What is the y-intercept for both of those graphs? Because they have the same one. What do you think? It's 1. Okay, so for these two graphs, I'm going to write 0, 1. In general, I don't have a number in front of what we took to the exponent, but I just want to put this on here. In general, it actually should be 0, whatever your a value is. because if you plug in 0 as x for your exponent, anything to the 0 power is 1. The two graphs we have here today, they're both 0, 1. But if we had a number for a other than 1, that would be the y-intercept. Okay, now, underneath, I'm going to try and see if I can slide this on here. Okay, both of these graphs have the same domain. Can anybody tell me what, left and right, what your possible x values are here? What do you think? Yes, negative infinity to infinity. If you want to write all real numbers, and that's true for any exponential graph. There's no restriction other than we're not going to plug in imaginary numbers. There's no restriction on what you can plug in for your x value. Now, the range for both of these graphs is the same also. They are graphed a little bit differently, obviously, but they have the same range. What would you tell me the range is for both of these graphs? So if I go, either one of these, if I go from the bottom to the top to describe an interval, what y values are we touching for both of those graphs? What do we think? What's the first y value touch? Yeah. I go up to infinity, right? It goes up to infinity. Both of them go up to infinity. What would you put on the bottom of this interval? Okay, super tricky, right? Because I told you it's not going to actually touch the x-axis. It's not going to go over it. Okay, so here's how we handle this. I'm going to write 0, but we don't actually touch 0 because these fractions on either side of these graphs would just get tinier and tinier and tinier. They don't actually become 0. They never become negative. So all you do to take care of that, instead of using a bracket, because I don't actually touch 0, we're just going to use a parenthesis. And all these graphs will be like that. The range will be a parenthesis around whatever the lowest value is. Some of these are going to be shifted. We're going to do that tomorrow a little bit. But the lowest value, I don't actually touch 0 because I get really close to that line, but I don't touch it and I don't go over it. And that is going to relate to this lovely word right here. This is called an asymptote. And you have that in both of these graphs, and it's actually the same for both graphs. But this is a line, a graph approaches. So both of those little J shapes, one's forward, one's backwards, they get really close to that x-axis, but they don't touch it, don't go over it. So it's a line that a graph approaches, doesn't actually touch or cross that line, which is maybe a little bit redundant, but it doesn't actually get to that line. It never goes over it, it's kind of bounded by that line, if that makes sense. Now, both of these graphs have the exact same asymptote. It's just the x-axis, right? So the actual equation is y equals 0. It's a nice horizontal line. All the y coordinates are 0. It is going to be the x-axis, but the actual equation of that x-axis is y equals 0. Okay, is anybody having a question about the graph so far? Okay, now what we're going to do here for the rest of this is do a little bit more with just exponential equations. So it just says without graphing these, we're going to determine whether we have exponential growth or decay, and we're going to state the y-intercept for each. So exponential growth is if your b value is bigger than 1, and exponential decay is if your b value is between 0 and 1. So what do you guys think for this first graph? What would you tell me? Growth or decay? I have 100 times 0.78 to the x. Growth or decay? This one's decay. All right. 0.78 is between 0 and 1. All right, now my a value here is 100, so that's not going to be a determining factor in whether it's growth or decay. It's totally based on the b value. It does ask you real quick right here, state the y-intercept for the graph. Okay, y-intercept for any graph happens when the x value is 0. So if I plug in, we have 0.78 to the 0. Now, the most major mistake people make on these questions when we're working with exponentials, they'll take and they'll do 100 times 0.78, and then they'll do that to the 0 power. Okay, I want you to think about your order of operations, all right? So order of operations, the exponent would come before you would do the multiplication. So that's why we'll have those numbers kind of separated, like they'll have a little parenthesis, because only the 0.78 is being taken to that power. Okay, Anything to the 0 power is what? 1. All right, so that literally just wipes that out, and you would just be left with whatever the a value is. So anytime you have a y-intercept for an exponential, if it's not shifted or anything, we just have an x in the exponent, then it should just be 0, whatever the a value is. That'll be your y-intercept. All right, what do you guys think for this one, growth or decay? This one's growth. If it's bigger than 1, it's growth. What would my y-intercept be for that second equation? Yes, ma'am, 0, 16. Good deal. All you have to do, if you're not sure, just plug in 0 for x. Now, what do we think for this last one, growth or decay? Growth, right? It's bigger than 1. What's my y-intercept for that graph? 0 what? 4. Just 0 and then the a value. And if you don't believe me, plug in 0. I promise it'll be true. Is anybody having a question about any of those? Okay, now that b value, whether it's growth or decay, is determined by these little tiny formulas here, just generally if we have an actual situation for a question, which we're going to do more on the back. But I want to talk about each one of these. What's the percentage of growth or decay? So like if it's decay, how much are we taking away? If it's growth, how much are we increasing by? So what I mean by that, this first one we said was decay, and you absolutely don't have to use a formula to do this, but I'm going to show you this. This first one we said was decay. So my b value was 0.78, and that's going to be 1 minus the rate of whatever we're taking away. All right, so if I subtract 1, just real quick, from both sides, that's going to give me a negative number, which would be negative, let's see, 0.22, and that would be the negative version, because it was 1 minus my rate, so it would be the negative version of my rate. So I would say 0.22 is my rate. Do you guys know how to change that to a percent? Like, what would I do to change? That's a rate. How do I change that to a percent? You remember? Because it says it wants the percentage of growth or decay. Yeah. Perfect. Okay. So all you got to do, times this by 100. That first one is representing 22% decay. Now, to me, I don't like plug it into that little formula, right? Like I look at that and I think, okay, that's a 78% like on a test is what I look at that. And I'm thinking, okay, what percentage did I lose? So I lost 22%. That's kind of how I think about it. If you have growth, which I have in the other two here, my b value, which was 1.35, is 1 plus the rate. Anything over 1 is going to increase the value. That maybe is a little bit, if you want to use the little formula, that's a little bit quicker to see. So this would be 0.35 as my rate. And again, if you want to change it to a percent, we're just going to multiply it by 100 real quick. So this would be a 35% growth if you had 1.35. The 1 accounts for whatever you already have, and then the 0.35 adds 35%. Now, the last one is kind of tricky. So the last one we said was growth, right? So my b value, which was 2, is 1 plus my rate. So if I subtract 1 from both sides there to get my rate, if my rate is 1, what percentage increase would that be? 100, yeah, for sure. This is 100% growth. Is anybody having a question? All right. Whatever it is over 1 multiplied by 100, whatever it is, if you got the decimal there, like I had the 0.22, you're going to, same thing, it's just decay. Okay, now, we're going to write some equations for the rest of these, and this is where you might want your calculator, because these lovely formulas are not always the greatest. Okay, so we're going to use that general form, y equals ab to the x. Now, in general, I'm just going to write this real quick. A for any of these is going to be an initial amount or a starting amount. B, depending on the question, is going to be your growth or decay factor, and we'll have to determine that based on the context of what's going on in the equation, or in the information in the problem. And X is going to be time for all these questions. Okay, So this first guy says population of a city is 180,000 people and is decreasing at a rate of 5% a year. Okay, so the A value, I can see it right away. It's just going to be the initial amount, the 180,000 people. That's going to be my A value. That's what I'm starting with. Okay, now it says it's decreasing at a rate of 5% every year. So if I'm decreasing, am I going to have exponential growth or decay? If I'm decreasing. Decay, okay, thank you. Yes, all right. Sometimes the words are tricky, but decreasing is not too bad. Okay, decreasing is going down, right? So every year we're going to lose 5% of the population. Okay, if you want to do the actual little formula, your B value is going to be 1 minus the rate. Most of the time, not always, but most of the time these questions will give you the rate as a percentage. So this one says it's decreasing at a rate of 5%. Do you guys, we want to use the rate, which is the decimal. Do you guys know how to change a percent to a decimal? Do you remember doing that? Okay, if you have the percent, if you're like, I don't remember, you're going to do whatever the percent is, it's 5 here, and just divide that by 100. It scooches the decimal place over 2 spots. In this case, this would be 1 minus 0.05. So I want you to think about this for a second. If I take 5% away, if you had a test and you took 5% away, what would you get on the test? 95, right? So that's what you're going to have here. Anytime you have decay, it's like I'm just going to take that away, but I still am going to hold 95% of my population. We're just going to lose 5% every year. So if I want to write a model for this, I'm just going to write y equals, we start with our initial amount, that 180,000, and then your B value, don't multiply these together, we're going to keep them separate because we got to do the exponent first. It'd be 0.95 to the x. That could just be a general equation to represent the city's population. Now, all you have to do, usually they'll kind of ask you a secondary question, which is what's going to be right here. What's the population of the city after 6 years? Literally, all you're going to do is you're just going to plug in 6 for x. So in 6 years, how many people? Oh my goodness, my calculator is validating its operating system apparently. Okay, so this is where I'm going to grab my calculator. So 180,000 times 0.95 to the 6. And if you type it in right like that, you won't have to worry about messing up the order of operations or anything because the calculator will do it correctly for you. And I'm going to have us, because we're talking about people, I'm going to just round to the nearest whole number. So I'm going to say that's going to be about 132,317 people. And if it doesn't tell you, just round to what would be reasonable for the question. So like I can't have part of a person, so that's why I'm going to round to the nearest whole number there. That's going to be exponential decay. All right, now we're going to try exponential growth in this next one. So this says a house is purchased for $155,000. So that's going to be my initial amount. And it says it's appreciating in value. Is the word appreciating going to mean to you we're going to be raising the amount or lowering the amount? Raising, right? Okay, appreciating is increasing. So this is going to be, if you want to use that little formula, it's 1 plus the rate. Basically what goes on there is the 1 accounts for what you already have and then adds on whatever the percent is. This is 3.5%. So my rate here is 0.035. All right, so what we're going to do here, this would just be, just in general, the worth of the house would be $155,000 times 1.035 to the x, and x would represent the number of years that they've had the house. And it says how much is the house going to be worth in 10 years. So all that means is we're going to plug in 10 for x to answer the question. I just want to show you just one thing real quick before I do that though. Okay, if I take 155,000, right, and if I multiply that by 0.035, what that means is the value of the house would go up by $5,425. Okay, now here's the deal. If I take and do that times 1.035, what the question actually, or what that does for me is that takes and just goes ahead, and instead of us having to do 2 separate steps and take 155,000 plus that 54 25. If I just do it with that 1.035, it adds that on for me. So that's where that 1 comes into play when you're doing any of these questions. So this is what we would add. If I do that 1.035, it just automatically tells me in that next year that's how much the house would increase. So that's why the 1 is involved in that. Anywho, so if we want to actually answer the question here, though, we're going to do that 1.035 to the 10th power. Now we're talking about the value of the house here, so because we're talking about money, I'm going to go 2 decimal places. So $218,642.81. Anybody have a question? Okay, so decay, do 1 minus the rate, growth, do 1 plus the rate, and the 1 is just to account for what you already have with your starting value for your A. Excuse me. Okay, now I put this on here on purpose because I've seen a question like this. It's a little bit weird. So it says an investment is worth $56,578 after 8 years. So they're giving you here, this is not an initial amount. This is the Y value here. This is what the house is worth, or the investment, sorry, that investment is worth after 8 years. So 8 years, the time, they're also giving you the X. Okay, now it specifically says the growth factor. All right, it does not have a percentage along with this, so growth or decay, if they have the word factor involved in that, there's no percentage symbol. They're trying to say straight up, like, this is the B value. That's what they're trying to say. And then this one actually asks you to find the original amount that you invested. So A is actually going to be our variable when you set this question up. So I'm going to use that same format, y equals AB to the x. I know y here, this 56,578. We don't know the initial investment. That's what we're working backwards to figure out. I don't have to calculate anything for the B value. They're just saying it's 1.15, not a percentage listed or anything like that. It just says growth factor. My exponent is, sorry, that y is kind of really close to that. My exponent, actually, I know that as well because it says after 8 years, so I know that would be 8. Now, you can literally just do this in one step. Just divide both sides by 1.15 to the 8th power. And that'll tell you the original investment. You can just do it right on your calculator. You don't have to do anything fancy here. Okay, so I'm going to do 56,578 divided by 1.15 to the 8th. And your calculator will do the order of operations there for you. So it'll do that 1.15 to the 8th first, and then it will take whatever that is and divide that, bless you, that 56,578. All right, now we're talking about money again. So I'm going to say $18,495 and about 45 cents. After 8 years, to take your money from 18,000 something to 56, that's a pretty good investment. Now this says, just kind of a secondary question, what's the percentage increase the investment earns every year? So I know I put in this $18,495. How much interest does that earn every year? Can you guys tell? How'd you get that? Yes. Yes. Yes, yes, yes. Okay, there's your B value. So whatever it is over 1.15, just take that, multiply it by 100, and that'll give you the percentage. So it's earning 15%. That's pretty darn good. All right, now I have one thing left real quickly, and I will give you guys all these formulas like tests, quizzes, whatever. They're typed into the questions and things like that, but I'm going to write this out for you. If any of you guys are in chemistry, maybe even biology would talk about this too, but a half-life is just kind of a little bit of a modified form of an exponential. So in general, all right, y equals A, still going to be your initial amount. When you talk about a half-life, it's the time it takes for a substance to get cut in half is what it is. In the case of a half-life, your B value, it's always going to be 50% decay, so it's always going to be a half. So anytime you do a half-life formula, you don't have to figure out the B value. It should just be a half. Now, the other thing that's a little bit weird here, the exponent's just a tiny bit different. Instead of just being a plain x, it's x over whatever the half-life of the substance is. Okay, and I'm just going to make one little note on this. X is time, right? X has to be the same units as the half-life. So if they're talking to you about a substance and they're like, okay, the half-life is in hours, then your X value has to be in hours. If they're talking to you and they say, okay, the half-life is so many years, then the X has to be in years. So those two things have to be in the same units. So I got a question down here that doesn't have that, just so we can practice that. But really quickly, a lot of times these are like weirdly named substances that will have a number in the actual name. These are legitimate things. But basically don't use the number in the name of the element or whatever you're talking about. Don't use that in your formula. Okay, so it says hospital has a 50 milligrams supply of technetium 99. We're not using the 99 anywhere in this. And it has a half-life of 6 hours. So I'm just going to write a formula to represent the decay of this based on its half-life. All right, so our A value, we have 50 milligrams. Whenever you're doing a half-life problem, 0.5. And then its exponent is x over the half-life, which is going to be x over 6. So it'll be 6 hours. All right, now, see if you can just tell me this without really doing it. How much of the substance would remain after 6 hours? 25, right? Because in 6 hours, the half-life would cycle one time, right? So this would be 25 milligrams. This is a nice number. I just want you to think about this real quick. If I were to actually plug that into the formula, that's why the exponent is like this. So 6 over 6. After 6 hours, right, this would be 50 times 0.5 to the first. It would be 1 half-life, so it would be cut in half one time. All right? Anybody know just off the top of your head what it would be after 12 hours? Say that one more time. Yes, 12.5. You're just going to cut this in half again. All right, so 12.5 milligrams. Now, if you actually put it into the formula, right, you'd have 50 times 0.5, 12 over 6. That means our exponent would simplify to be 2, so it would be cut in half twice. Is that making sense why that exponent is that way? Okay, now, if it's not a night, like you guys figured that out pretty quickly, right? If I give you something like 15 hours, that's not like a full half-life, if that makes sense. So in that situation, I would actually for sure just use the formula. And don't think you're doing anything wrong, because a lot of times these have like really weird answers. So I'm just doing 50. Do that 0.5 in little parentheses. Now, this is important. If you can, like this on my calculator, right, I can see this exponent. I'm going to do 15 divided by 6. If you can't see that exponent, or if you're using a scientific calculator, you need to put parentheses around that 15 divided by 6. If you have an 83 or an 84 where you can't see the exponent, you have to put parentheses around that. Like maybe just try it on your calculator real quick and make sure you're getting the same thing I'm getting. I'm just going to go to 2 decimal places. I think that's what it says in the directions. You should get 8.84. What was this? This was in milligrams. If you're not getting that number, just, and I wish I could fix it on my calculator to do this. Just when you do your exponent, just put little parentheses around the 15 divided by 6, and then that should fix it. Is anybody having trouble with that? Okay, I'm going to do one more. Now, this one is just really put on here to make the point about we should not have different units when a half-life is in a certain unit and the time is given to you in a different unit, which is going to go on here. So this is I-123 used in thyroid scans, legitimate thing, has a half-life which is given to you as 13.2 hours. Write exponential decay function for a 350 milligram sample. So I got 360, I can't speak. So it'd be 360, we're doing half-life, so my B value is a half. And it says find the amount after 3 days. So here's the deal. If your half-life is in hours, then your X value, which is 3 days here, has to also be in hours. So what would you do with 3 days to convert that to hours? Yeah. Heck yeah. All right. Just going to multiply that by 24. You got to convert that to hours really quick. There's 24 hours in a day. So this would be 72 hours. That's the only thing you have to do. You have to make sure the units are the same. Most of the questions are not going to do that to you. If they do, I tried to put, like I did in this question where I bolded it so that would draw your attention. Now, if you are using a scientific calculator, you cannot, I'm going to do 72 divided by 13.2 here. You can't use the fraction key on a scientific calculator to do that exponent because you have a decimal as part of that exponent. So if you're using a scientific calculator, put parentheses around that and don't use the fraction key. And it should work. So we should have, I'm just going to go 2 decimal places again here, 8.21 milligrams left should be our answer. Does anybody have a question?